Begin with a way to see that if you apply many unitaries in a circuit, then the errors accumulate linearly. This we will try to show. So our this is the vague thing. We will make it what is error, what is linear. This we will we'll discuss it. So we so I will begin with the result that I want to intend to prove, and then we will discuss about the background concepts. So this is the thing that you would like to prove. So let a unitary operator U is formed by this. So you have to think of a circuit which has L operations, L unitaries, and so it's of course acts from this side. So here is the state. So first U1 acts, then U2, and so on, and the total action is given by this U. Where UK are unitary operations on some Hilbert space, on the relevant Hilbert space. So now, if each UK so it could happen that although I wanted to implement the UK, but in the process UK tilde was implemented. Or it could happen that my apparatus, my hardware is such that I can only implement UK tilde. This is not available to me for some technical reason. Okay, something like that is happening. But I should know how close this is to this, yes? And this is given by the precision delta K. It could happen that each one of them has a different precision. I haven't yet defined this word precision. We will define. So, but suppose this is a real number. These are matrices, of course. So we have to somehow define what is a precision. Then the product U tilde, which is U L tilde U L minus 1 tilde this thing, the approximate one, where every component has been replaced by an approximate version, each of them has a precision delta L, L minus 1 and so on. This approximates U with summation. So the errors add up. This is what I want to have. Well, the UK tilde, these were the unitary operators that I wanted to implement. I don't have them, I have the UK tildes, but they are of course themselves unitary as well. Because it's only unitary operators that are available to us. There's nothing else in nature. This is the thing that I wish to prove. You can show, we will not go in that direction, but that if the operations are not unitary, then the errors could propagate even faster than linear, and situation could be worse. So, this discussion is in this book, this Kitaev, Shen, Vialli, at page 70. So let us go back to find out what do I mean by precision. You may have done this, but I will repeat it for completeness. Something called the operator norm. It's clear that I have to define a distance between this UK and UK tilde in the space of unitaries. That distance I will get through the norm. And that norm I will call operator norm. It's called operator norm. The norm of an operator X called operator norm is, it's denoted by this, like for vectors. So what you do is, you take the operator and apply it on an arbitrary vector in the Hilbert space. Yes, I am not writing all this. So we are doing all this in some Hilbert space. This X is an operator on that Hilbert space, and this Xi is an operator, is a vector in that Hilbert space. Yes. So what I do is I see what is the, where does X take an arbitrary vector in the Hilbert space, and take the norm of that. So this will tell me what is the length of an arbitrary vector, but the vector itself could have been very big. So I divide by the norm of the vector. So this gives me the factor by which x takes xi2. Yes? So xi has a length, it has been multiplied by something, it has been operated on by this x, it is possibly rotated, increased or decreased, but I divide by the original length. So this gives me so originally it was something like this, finally it is something like this, it gives me the factor of the length. Yes? Of course, there are many vectors.
Like what factor the length has been increased?
Exactly. Take the supremum over all vectors. In quantum mechanics, there is no zero vector, but mathematicians also have zero vectors, so you take the supremum over all vectors that are not zero. Of course, you don't want to divide by zero. The zero vector is not the zero ket. I mean, zero ket is just a notation. The zero is the zero, which when is the null vector, which when added to any vector gives the vector itself.
Does it follow all the properties of a norm?
Yes, it does. So this is the thing that we will look at. So I'm not writing that, but I mean, you understand this discussion, yes? So it is roughly the maximum distance to which a normalized vector is thrown to. Yes? You pick up any book of analysis and they have quite a long discussion, important discussions on this. So it's good to know some of the properties because they will be useful. This, first of all, you have to see whether it defining properties, whether it can be called a norm. So, number one is you can show that this is equal to 0 if x is the zero vector and is greater than 0 if x is not the zero operator. I'm not proving all this, okay? You try to prove them. C is the field thing. We are always talking about complex numbers, so this is complex. Some other properties. Norm x square this last one is, well, this one is E, is often useful.
So the largest eigenvalue of x dagger x and x dagger will be same. The norm of x dagger
I
x.
think the norm of the largest eigenvalue, x dagger x and x dagger, they are different, but their largest eigenvalue, I guess, will be the same. True. The question is if are the eigenvalues of x dagger x and x dagger the same?
Not all eigenvalues, just the largest eigenvalue.
This is what I'm thinking. No, I mean, I was writing this because this is the form that we need in quantum mechanics. But intuitively, I would think that what is the difference between these two? Why should this be more important? Is there something here?
So can we think in a way like if we take x as the creation operator, let's say in quantum mechanics, can we have some?
So if I replace this x by x dagger, I get that, no? And x dagger norm is this. X dagger norm is the same as x norm. If I replace x by x dagger, I get x dagger. So at least the largest eigenvalue is the same. I don't know whether all the eigenvalues are the same.
If all the eigenvalues were same, we could have gotten one from another using a unitary transformation.
That is true.
But that is probably not true for any arbitrary matrix X.
Why?
I don't know.
Yeah, I don't know. The eigenvectors could still be different. Eigenvalues could be the same. I don't know. But well, at least the largest eigenvalue are the same. If these two, if you use these two will have the same largest eigenvalue.
So what happens to eigenvalues of a matrix when you take the Hermitian conjugate?
Eigenvalues of a matrix. Well, you will get the. It depends on what type of matrix it is. If it is a normal operator, so that you can write the spectral decomposition, you just take the Hermitian conjugate of both sides. So you can get the complex conjugation of the eigenvalues.
If it's norm.
And this one is that this is equal to 1 if okay. So now once we have the norm, we can find out the distance between operators, including distance between unitary operations. And this delta that we are talking about, the meaning of the precision is exactly that. So we will have a definition that by the word precision, we will mean the distance between unitaries. So we have already stated one result before this. Let me state another. So let us call that Theorem 1, and this one is Theorem 2, is that if U tilde approximates U with precision delta, then the inverse of this approximates U with the same precision. So it says that if you are in a circuit, if you go from one state to another and you come back by its inverse, provided the both are available, going there and coming back, these operations are available, then you have delta this way and delta coming back. So you have an error, but it grows linear. The proofs of this theorem form assignment 1. You decide the deadline.
Theorem 1 and 2.
The one was the theorem that I did not mark as theorem 1.
Prove that every
The proofs.
is linear.
Exactly. The proof is given in this Kitaev's book.
Yeah, that's not going to help.
Hmm?
That's not going to help.
It's in English.
Fine. I mean, I would request you to do. I mean, this does not form the assignment, but do these things as well, these properties as well. But don't submit it as an assignment. Poor Ratul has to check a lot of things then. But and you people have to also write it carefully and so on. Fine. Okay. Have any questions? Because I will start something new.
Sir, you wrote the statement that U tilde inverse approximates U with delta. So how the statement will change, like if I compare U tilde inverse with approximation with U inverse?
Sorry, there was a typo here. Sorry, this was an inverse here. Any questions? Defining lengths of operators is interesting actually. So you can try to find out whether you can by yourself define a new length and then try to see whether this linear propagation holds for that norm as well.
Instead of supremum, sum.
Pardon?
Instead of supremum,
Hmm?
sum.
Sum of what?
Summation over all the bases.
All the, but there are many bases.
No, here you are doing a summation supremum over basis, right?
No, it was all states.
Right. You will get the value. That is much harder, right?
It is.
So how, if I give you a matrix and ask you what is the norm of this,
Well, there was this eigenvalue thing.
largest eigenvalue.
But yes, for a general matrix, it can be a hard problem. Finding an eigenvalue can be difficult for some operators. We will start something new. We'll use the phase estimation problem. The phase estimation algorithm, the quantum phase estimation algorithm. Everything is quantum, I'm not writing quantum anymore. This is at section 13.2 of this book. So we will define what do I mean by phase estimation. It's the phase of a unitary that I want to estimate for a given eigenvalue, for a given eigenstate. So at this moment it is of course not clear why I want to do that. It will become clear maybe 2 days later. So currently the problem is the following, that I have a unitary, there is a circuit, it can be big one, there can be many qubits involved, and there is a unitary in it that I can operate on that. So, and there is an eigenvector that is given to me in some way, I will tell you how. And the problem is to find out the eigenvalue. Now the unitary operators have eigenvalues of the form e power I phi, this type. So I want to find that phi. So that is the phase. Unitary operators have eigenvalue in forms of phases, yes? They are all of modulus 1. So I want to find that phi. That is the phase estimation that I want to do. For a given unitary and a given eigenvector of it, I want to find its phase, the phi of the e power I.
So we already have the eigenvector.
Eigenvector is given and the unitary is given. I want to find the experimental. Find out the phi. So let U be a unitary on n qubits. Yes? So if you do read the book by Kitaev and others, you have to remember that this notation there is like this. They denote qubits with a curly b, and then this becomes this. Okay? notation are a bit different than we are used to in quantum information. In the usual papers that we read. Let U, this is a unitary, so I can always write it in spectral decomposition. Yes, this J equals 1 up to 2 power n. This is the dimension. So there are so many eigenvectors. These are eigenvectors. And this is the phase. So it will be e power I multiplied by a real number, but I will write it as twice pi I. This is just to make this lie between 0 and 1. There will be hanging 2 pi around all the time, so I just remove it. Let this be spectral decomposition of U with one is the same as 0, yes? The problem is to find the theta for a given psi that is promised to be an eigenstate of U. Okay? So we know that U psi is theta for some theta belonging to 0, 1. The problem is to find theta. This is still ill-posed. The statement is still ill-posed because we haven't defined up to what precision that we need theta to. This we'll do later as we go on. You see, theta is a real number, well, at least a rational number. I mean, in experiments, we will find up to some precision, so these will be all rational numbers, but still it's an infinity. Fine. Questions? some notation here. Lambda m u. It is a new unitary. It of course depends on this unitary. So remember this u was in C2 tensor n qubits. This is a bigger animal. So it is an additional n qubits. It is defined as this acts some k phi. This part is here, this part is here. K runs from 0, 1 up to 2 power m minus 1. So there are 2 power m things from here. This is a basis there. Phi is an in this. This is a control unitary. This thing is left intact. This other part is operated k times depending on this k on the okay. So for an arbitrary state to see its action, you first of all leave this as it was, and this one has to be acted on by this unitary in the function so many times as that key.
So it's of the form identity tensors.
No. Certainly not. This is left, it is like the C0 gate. C0 gate is not identity times something. Yes?
It has K control bits, M control bits.
It has M control bits, but the control acts in this specific way. In the C0 it acts in some other way. Remember the C0? Yes? So it has a lot of similarities with that. You first of all keep this thing intact in the C0. Yes? But this one changes depending on what was here. This one, if it was 0, nothing happens. If it is 1, then it is flipped. Yes? This is not the same as identity times some operation. It cannot be written like this. To prove that, you can show that this C0 can create entanglement out of a product state. Whereas this will never create an entangled state out of a product state. Yes? So this is of course not the same, but it's similar in the sense that there is a thing that is kept intact, and the other thing, this is called the control and this is called the target. Here the target is this entire thing, but the action on the target is of course very different.
So this one is a global operator?
This one cannot be, yeah, it's not a local unitary, it's a global unitary. It's not only it's not like this, it is not even like that. You can never write it like that because this never creates any entanglement. And you can show that this operation actually creates entanglement. In this basis it does not, but if you take a superposition of these, some of these, you will get an entangled state at the other end.
After applying zero.
After applying, so you check this, which two should you take, this one and this one, no?
No,
Yes.
take 0, 0, put Hadamard and 0.
Yeah, but you can see it like this as well.
Zero,
Just apply it to the sum of these two,
Yeah.
which is actually what you were saying.
Yeah.
So, but now you see that you have the state as 0 plus 1 and a 0 on the other, on the target. This will go to 0, 0 plus 1, 1. Yeah. And this is an entangled state. This is not an entangled state. So this is the operation that we will use to do the phase estimation. So such that this in circuit diagrams, they usually denote it like this. This is the usual notation for.
That is actually M complexity rather than just one. It order
Once more.
like each such operation of lambda M will require M black boxes.
This is a single unitary that we are taking.
So
You mean you will
larger
decompose it?
Yeah.
You want to decompose it and see how many unitaries it takes?
It will take. It has to take M units, right? To create one lambda M operation.
So, but you should not think of it like that because it has to act on the superposition as a whole.
Yeah, definitely.
When the superposition is coming, you cannot apply U on one of them and the other one because they are coming together.
Yeah, so it's a combined process.
Exactly.
But to create lambda M, if the complexity of the problem has to be calculated in U, in terms of how many U's are required,
Exactly.
users of U, that will be M. Each lambda M costs M U's.
No, this is not clear. This is what I'm saying. So, first of all, the complexity of this is not calculated in terms of the U's, but it is because this U is a big unitary on this end. It is calculated in terms of how many qubit unitary, 2 qubit unitaries and single qubit unitaries that you, because those are the ones that are usually available in experiments. And the other fact is that this we have not done, that with single qubit unitaries and 2 qubit unitaries you can implement every unitary. But what I also want to say is that although this when we will finally do the operation, we will give the system a superposition of such states where different Ks will appear. Now, that thing will come at a single go. So it is not clear how you will operate 5 U's in one term and 6 U's in the other. It's not, so if you have 5 U's and 6 U's available to you, it is not clear how will you apply that to two terms in the superposition. So it is good to think of this lambda mu as a single entity.
Can't you do something like each of the k bits in those each of the m bits, you apply a control and I controlled u. A control on each bit with a u acting on phi. So if it's
This I don't know. It may have. You mean to say that each of them will act with a unitary? Whether that is not very clear whether that will work. So you mean to say that you act with a unitary here with one of them?
each of
That is not clear, no, because these lines are, each of these lines are single qubits, and whether different unitaries will be able to do this, I am not sure about that. I think it has the same problem because it will become a product unitary over such things, and this one is not a product unitary.
Yeah, it's the same thing what we were discussing, right? He's asking to put a control. Other we were discussing identity versus, yeah,
So
it's the same problem.
this
It's not
will
possible.
not possible. Unless there are things like you have a unitary with this, and then you have a unitary here with the same thing. I mean, with a different thing. If you have unitary here and here, and here and here, this I think will not work. If you apply here, here, and with two here, then that may work. But it is not clear whether that will be optimal. So optimizing this is a difficult problem. If we have time, we can go there. One has to finally show that all this thing is polynomial in the number of unitaries that you act. Otherwise, the whole thing will fail. Because we were finally going to use it for the Shor algorithm. So if there is an exponential thing that is hidden somewhere inside, you will be defeated.
So polynomial in what? The number of qubits.
Polynomial in the number of unitaries that you implement on the qubits, the single and 2 qubit unitaries. So, but that is far away. So we come back here. So yeah, this is the notation, and so now we write down the circuit that will do the phase estimation. So just for the notation, whenever I put 3 lines, you should think of it as n qubits. And whenever I put 4 lines, it is n qubits, okay? So you remember that our lambda mu was an operator that acts on C2 tensor M tensor C2 tensor N, and this is the control and this is the target. So I will finally implement the lambda mu, but that is somewhere there. Before that, I begin. This is the psi that is given to me as an eigenvector of the u, not of lambda mu, of the u. So that, if you remember, it was an n qubit system. The u is an n qubit unitary, psi is an n qubit vector. I take m qubits in the standard state, 0 everywhere. 0 is the computational basis vector. You can think of it as the z basis or something, upspin in the z basis something. Okay, this one. This is my beginning thing. This is my input. This is given to me, and I prepare this. And as always, we act first with Hadamard to go to the quantum. We hope that this will create a quantum. We know that this will create a quantum parallelism, but we hope that it will be useful for us to use that quantum parallelism. Yes, we do nothing to this up to now, but then we apply this lambda m. Okay. We will do something here, we will mention that later on. This is the circuit. We haven't specified what this is, we'll come to that later. So, there are these 4 stages, if you say. So, we call them psi 1, psi 2, psi 4. There will be a measurement at the end, we haven't yet mentioned that. So, this state is just this. This one is Hadamard rotated, so it's essentially plus tensor M, yes? We will write it as the sum of all combinations of bits, this k, and then you make the qubit out of it. It's like 0 plus 1, 0 plus 1, it will be 0, 0 plus 0, 1 plus 1, 0 plus 1. So all combinations of bits in the qubits, of course. And this is the normalization. This will 1 by root 2 power 2. So it's 1 by root 2 power n.
Is that the 2-dimensional Hadamard that will create the entire superposition?
Tensor M of them.
Yeah.
So it's actually misleading to write it like that. But so it's actually these are all H. So they don't talk to each other until here. Now, now we come here. So this is just a u power k here, yes? So it is there's a tensor product here, just like here. Not writing that. Tensor product here. Better to put a bracket. Now you remember that psi is an eigenstate of the U. It's not just an arbitrary unitary. Yes, this we wrote maybe 2 times already. And this is the theta that we need to find. So, this uk on psi is just e power twice pi I k theta psi. So, this thing just after the big control unitary, at stage 3, it is the tensor product that was here, and now it's here. This doesn't depend on K. This bracket is not required, I'm just putting it. But I put it because come back here. Throw them out. So we have gotten rid of this last 10. But the first term is still here. We have still not defined this. So we can forget about this last part. We are only here. We will do something here and here. We are at the moment here, and the state here is the state within the bracket. We'll do a special case first. Theta is the thing that we need to find. And then suppose someone has given me the u and the theta, and then later on I somehow got the information of the person was benevolent or something and told me that it is always of the form some integer divided by 2 power n. This I was told. This is a special case. You'll see why. Maybe you already understand. But for j equals j belonging to in this set. So j is in this set and all of them are divided by 2 power n. So you remember that theta has to belong to 0 to 1. So this satisfies that property. We're doing that. So in that case, the final state, final meaning the state here, removing the last n qubits is this thing, but that can be written as I just put, in place of theta, I put this thing. This e power twice pi I over 2 power m is 2mth root of unity, yes? It's fine? Call it an omega. Put it here. Just notation.
So that one. W is equals to
2 pi I over 2 power m
is a
is a 2mth. 2mth root of unity. Third root, fourth root.
So in this case, the state psi 3, what is that? Bereft or what is it?
Bereft, without.
Without, bereft.
I think there is a off missing. So let us give it a notation. Let this thing, exactly. So since I have been promised that this theta is of the form j over 2 power m, where j is 0, 1, 2 up to this 2 power m minus 1, I know that the state here is one of them. Yeah, for one of the j's. Because I have been promised that it's there, the theta is already given among these. So we know that the first m qubits of our circuit at stage 3 here is for j equals 0, 1, 2 and so on. Now, let us calculate this quantity for some j and j prime. Yes. Yes. The j prime is on this side. J is a bra, so it will become a minus. Okay. The geometric series, you can do this. can check that this is equal to 0. Check this one. Since this phi j, well, I mean, since these are orthonormal, you can think that you will just make a measurement in that basis, find out the j, and that's it. We wanted to find the j only, right? Theta was already of the form j by 2 power m. 2 power m I know, so I want to find the j. So here, I have realized that my states are of this form. So I will just make a measurement in this basis, in the basis of the phi j's, and we are done. We'll find the j. But in circuits, we usually do not want to make a measurement in this type because this is very difficult actually. So we implement some unitary to bring it to the complementary basis, to the computational basis. And as you realize, this is actually a Fourier rotated basis from the computational basis. So you have to apply the inverse Fourier transform on this, the discrete inverse Fourier transform on this, to bring it to the computational basis. So you have to bring this to G. J to this is the Fourier transform. This is the inverse Fourier transform. So this is what we will do. But the point is that we have already found the J, but in the special case. So just a few more lines. Since these are orthonormal, there exists a transformation F such that f of j equals to phi j, the discrete quantum Fourier transform. So this box that was empty until now is actually quantum Fourier transform and n qubit quantum Fourier transform diagram. So this is, without the dagger is this F. So this psi 4 without the last n qubits is psi. So if you take it along with the last 10 qubits, it will be j tensor psi. So it's the same thing that is dumped here. So we find out, you make a measurement in the j basis. So here, this was dump, and here this is measurement in this basis. So whichever clicks, you take that bit j, that m bits j, and the answer is j by 2 power. Yes. Okay. This is what we have to answer now. So if theta happens to be of this j by 2m form, things work out fine. We'll now go to the j not equals j by 2m form. Question?
Yeah, what is the form of it?
Pardon?
What is the form of f? I mean, well, how can I write f as an expression?
Well, just take the inner products of phi j with the j's, you will have lots of omegas, huge matrix. Depends on which basis you are writing. Suppose you are writing in the j basis, so you take a j prime on this side, so you'll have a j prime here, and the j prime when it comes here, these are all orthonormal, so you will have these along with these. This you can keep outside, so you will have a lot of omegas throughout. More questions? Okay. You do this next day.